Hello everyone, the purpose of this video is to give you a better understanding of the relationship between the electric field, E, and the electric potential, V. And we'll do this through an example, exercise 2361 in Young and Friedman 13. Now, the setup of the exercise is the following. We have two metal cylinders, one of radius A, infinitely long, and one of radius B, infinitely long, with opposite line charge densities plus lambda and minus lambda. And we are asked to find the potential of this configuration with the restriction that the ground of the potential is at the outer cylinder. Okay, so that's the setup. Now, first we have to think about the exercise. That's the first step. And this is what they, in Young and Friedman, call setup. Now, from Gauss' law and the symmetry of the configuration, we can quite easily find the electric field in the three regions. Within radius A, in here, the electric field is 0. In between, it's proportional to 1 over the distance, and beyond the two cylinders, it's 0 again. Okay, and now let us calculate the electric potential V. So the electric potential V of R is then the electric potential of point V minus the one at VB. Because this is 0. And by definition, this is the line integral of the electric field between these 2 points. Now, we'll use that the electric field is radially outward of the cylinder and choose a path of integration that is also radially outward. So here we choose radial integration path. And then we use that the electric field is parallel to that direction. So we simply get the magnitude of the electric field integrated from R to B. And then we get 3 different results depending on what region we're in. So within the inner cylinder for a radius R less than A, what we get is the following. And I write up the formula again, because this is really the connection I want to stress. Now we can divide this integral up to a part from R to A and a part from A to B. Okay, and then we can use that the electric field is 0 in the inner region. This here is 0, the electric field there. Here. Now, the second part is then, of course, something that is independent of R. We'll comment on that in a moment. And we put in the specific form of the electric field, looks like this. Now, during the integral of 1 over R, we get the natural logarithm. So the result is simply ln to B over R. B over A, sorry. In the middle region where A is less than R and that is less than B, we of course have the same formula, and I'll write it again. Now, however, the electric field is given by this expression, proportional to 1 over R in the entire region. And so we see that it's actually this integral we're performing now, but with A replaced by R. So the result is also just the above, but A replaced by R. And as we will see in a moment, this is a decreasing function of R. And then finally, in the last part, where R is greater than B, here the potential, again, is the integral of the electric field from R to B. But in the outer region, the electric field is zero. It's zero. So the result here is simply that the potential is zero. Okay, so let us try and draw this potential. Okay, now mark the points A and B here of significance. Then I will draw the potential divided by the value in R equal to A. So V divided by V of A. Now, for R less than A, we go up and read out the expression. It's a constant, and it's, of course, V of A. So dividing that out, we just get a 1 until we reach A. And then we get an expression that's proportional to ln B over R, so that decreases. And then when R is equal to B, we get ln to 1, so we get 0. And that's also what we get in the outer region. So there it's just along the axis here. Okay, now what you immediately notice is that the potential is constant in two regions. And in these two regions, the electric field is 0. Now, I want you to notice that the potential is not necessarily 0. I've noticed that that's a mistake you commonly make, that you think that if the electric field is 0, the potential must be as well. But that is actually not the case. The potential just has to be constant, but it can be non-zero. Okay, so the rule that is after it, and which simply comes from seeing that the potential is the integral of E, is that if the electric field is 0 in a region of space, then V is constant in that region of space, as you can see here. Now, oppositely, we can ask, what if the potential is constant in the region? Is the electric field then 0? And actually it turns out to be the case, because we know that the electric field is minus the gradient of V. Now I'll remind you that the gradient is just this vector differential of V. Okay, so V is constant, we're deriving a constant, which is 0. Okay, so we can use this to say that if the potential is constant, then the electric field is 0. Okay, so this is a very robust rule, but again I'll remind you that the potential does not have to be 0 even though the electric field is 0. The rule simply says that if the electric field is 0, then V is constant, and the reverse. Yes, thank you for your attention.